don't know, it just seems to work. So we have written here, we have a bunch of derivatives. We can simplify this a little bit. So note here we have the partial derivative of the position of this parcel in the x direction with respect to time. Now, I was going to do a little call and response section here, but I don't think it's too hard to see, in the interest of time, that that partial derivative is just nothing but the x component of the velocity. Okay? And similarly, the y derivative, the y partial with respect to time, is the y component of velocity, and so on and so forth. So we can then simplify this to write del u del t plus u, as in u, not vector, but u, the x component of vector u. The notation is great. You know, this is what we have. Multiplied by, or the partial x u plus v partial y u plus w partial u z. Okay, now, who here knows what the dot product is? Put up your hand if you know what the dot product is. Perfect, perfect. And who here knows what this thing is? If I write a nabla, does anybody know what a nabla is? Okay, so this thing is a pretty often used tool in vector calculus. It's not really a vector, it's a vector operator, and it's useful for a lot of reasons. It's useful mostly in just writing really nice notation. So what it is it's like a vector, but instead of having numbers along each component, it has derivatives along each component. And when you mix it in with vector objects, those derivatives get applied to each component as a vector would. So that's what the nabla operator is going to be. Now, if you really stare at this thing, you will notice that this is actually just the velocity vector dot product with the nabla operator. Okay, you can see here like the u gets matched to the x derivative, the v gets matched to the y derivative, and so on and so forth. So what we can do, now we'll start making physical sense again. We're through most of the notation. We can write u dot grad nabla, I need to say, shouldn't mix up terminology. Del u by del t plus u dot grad u. Okay? So what does this mean? Now we've turned this weird total derivative into this strange vector calculus thing. Everybody has a clear view on this, right? That's all good? Okay, perfect. So how can we understand this? So as I said before, we want to understand how the total quantity of this parcel changes with respect to time following a set parcel in the fluid, okay? Now that could be due to two things. That could be due to the parcel actually just having the quantity change with time. So this first term in the total derivative just describes the change with respect to time, keeping all else fixed. The second term is called the advection term, and it's very important in fluid dynamics. It describes the change due to a parcel as it moves from place to place, not due to a change in time, but due to motion from one region to another. Okay? So what we represent that is as the velocity vector dotted with the nabla operator. So what we can kind of intuitively see here is we have some notion mixed in to this spatial term in our derivative. We have some notion mixed in of the fluid is moving. If the velocity is zero, there will be no term here to describe the fluid's change with motion because it's not moving, of course. And then also mix in this nabla vector operator to include some notion of a derivative so that we can actually track changes with respect to time. Now, if we want to express this at every point in the fluid, what we'll do is we'll take this parcel here, which we've just calculated, how does it change with time and space. We'll take this and we'll shrink it down infinitesimally small, and we'll evaluate this at every point in the fluid, so that these no longer become derivatives acting on a fixed object, like in first year physics, but now they are vector partial differential vector operators acting at each point in a field. And then we can express this per unit volume. Of course, the mass per unit volume is the density. So on the left-hand side, we have the density times the acceleration. And now, it's kind of a little funky to go to this step, but this is not just MA for a single point in the fluid. We are simultaneously writing rho del U del T, or not, rho du dt at every point. So these equations are going to apply at every point in the fluid, okay? And so these rho and U are truly fields which are defined at every point in the fluid, okay? So that's this first term. So now we've got the MA. And now, I'm just going to run through every term on the right-hand side. Actually, there's a little note here about notation. They might have told you that you can only take the gradient of a scalar quantity, but you know, they're really cowboys in fluid dynamics, so they don't really care about that. And what they do is they just take the gradient of each component of the vector. So when you take the gradient of a vector, I mean, this, you know, it's a little complicated, but you basically just take the gradient of each component, and then you kind of consider each component of the equation separately. So this equation here is describing a vector u, which has three components. So this can really be thought of as three equations, okay? Now, what about this second equation I've written here? I've just been talking about F equals ma, but what about this one? So actually, before I'll get into the forces acting on this fluid parcel, we're just going to get into, there's a little rule of the game, which is that you have to have conservation of mass. We don't know about E equals mc squared. We don't know about mass being created or destroyed. In these cases, of course, that doesn't happen in the ocean or in the atmosphere. That would be crazy. So you can't create or destroy mass. So instead, it has to be conserved. If mass, or if a bunch of air flows into a region, then the density in that region must increase. Now, who here said they've taken E and M? Like most people, right? So it's pretty similar to the continuity equation in electricity and magnetism. So where rho is now the charge density, it's common to write, this is kind of like the fifth beetle of Maxwell's equations, the continuity equation, is that the change in charge density at a point is equal to the divergence of the current. I mean, if you don't know what the divergence is, I apologize. This maybe isn't super meaningful, but it's really intuitive. You can just think about it like the divergence, you know. That word has an English meaning. If the fluid diverges out of a point, or if it converges into a point, that will be described by this mathematical operation, okay? And so that's what this second equation describes. It only is a statement of conservation of mass, okay? But that is a whole half of Navier-Stokes. So I think this is the easy one, and then this is the hard one, people usually say. So, okay, now we can get into all of the forces. So the first force we have written here is pressure. That's, I should be specific. That's the pressure gradient force, okay? So what does that mean? Pressure is kind of a tricky thing to talk about in a fluid because it's got a lot of different effects, and it's not so easy to really intuitively define, in my opinion. But you can kind of feel it because we live in a fluid. Pressure is the amount that a fluid pushes out against a surface which it lies against. Now, it also pushes against other sections of the fluid. If you have a fluid with a region of high pressure, actually, to keep with an example we'll see later, let's call this a region of low pressure. What will happen is, fluids on the edge at a point where the pressure is decreasing, on one side there will be a really high pressure, and on the other side there will be a low pressure. And so, as I said before, you know, the pressure is how much a fluid pushes out against a surface. So it will feel a force downwards, the pressure, into regions of lower pressure. Now, this operator here, we're seeing it again, we're gonna see it all day. The Nabla operator, it describes to a very good degree, if you just put some scalar field on the right-hand side of it, if you just put like P there, and then you just take the P derivatives at each point, now this is a vector, and this vector, by the magic of the Nabla operator, it will point in the region, this will point in the direction where P is increasing. Okay, so essentially it'll say how much is it increasing in the x direction? Walk that much in the x direction. How much is it increasing in the y direction? Walk that much in the y direction, and so on and so forth. And what you get is that this thing points uphill in pressure fields. I mean, it's a little more complicated because it's three-dimensional, right? So you really have to think about it like it points not just uphill. The uphill-downhill analogy doesn't really work so well in 3D, but you can kind of understand what it means. Now, of course, as we just said, we want it to point downhill, so we actually use a negative sign. So this term just describes that a pressure, fluid, a section of a fluid will feel a force towards regions of lower pressure. Now notice, no matter what the pressure is, if it's constant, there is no force here. That's why it's called the pressure gradient force, because it only exists if there's a pressure gradient. Another analogy to electrodynamics, this is very similar to E is equal to negative grad V, where V is the electric potential and E is the electric field. Electric charges feel a force towards regions of lower electric potential. It's exactly the same thing. You can see it's exactly the same term. I want to make a caveat though. The pressure is not like the electric potential in any other way, basically. It's not like a potential energy, so it's more complicated, unfortunately. But that's how it works, okay? Okay. Oh, and feel free to interrupt. I mean, does anybody have any questions or thoughts on this? Yeah?
So in the mass conservation term, why is it there that you have to track the fluid as well? Like, why is it a capital V, not a partial V?
You're too clever. I don't remember. I think it's because this is done. It's done at a point with like infinitesimal, like you kind of it's like a quasi-static. You know what I mean? But I don't remember. It's kind of complicated. An important part here, which I kind of forgot, is that you got in the row here because this divergence really you want to talk about a mass flux. So it's not just the gradient, or it's not the divergence of U that you want. It's the divergence of rho U.
The rho dependence shows up, I guess.
Yeah.
Oh, another term. Okay.
The rho here is the mass. The rho here is describing the mass has to be, like an integral over rho over the entire fluid will end up being constant. Okay. Next up, you'd think this would be the easy one, but unfortunately gravity is also complicated because there's a little addition. So typically, right, for the most part, you just want to write Fg, this one's from high school, so everybody will know this one. This one is mgz hat with a minus. So if you feel a force of gravity down, and it's proportional to the acceleration due to gravity and the mass that you are. But I've added a little, I didn't write just this, okay? So this is felt by a fluid, of course. The fluid feels gravity. And it is expressed per unit volume, as I said. So this m is actually an m divided by v, which is the rho here, okay? But it's not so easy. So this is what we're gonna get into this now. I want to make it clear here. So these equations are expressed on the surface of the planet following the rotation of the Earth, okay? So what this means is, if you were to write F equals ma for a ball, right, or a piece of concrete or whatever, then you would want to, ideally, you would not want to be accelerating as you, like in your view of the thing, if you're accelerating, that will add complications because there will be extra terms. In order to understand what then will its acceleration be, there would be extra terms in the force which kind of would, add complications, right? Because there's going to be fictitious elements to the forces which you see the thing as having. This is why you want to write F equals ma in an inertial reference frame, which is not accelerating. However, in this case, unfortunately, the Earth is rotating, well, I mean, it's a good thing, but it makes the job harder. The Earth is rotating really quickly. And relative to the speed that the Earth rotates, the winds are not very fast. So if you were trying to write these equations and you were trying to do it from the perspective of a person standing off of the planet, looking down, not following the rotation, then you would see the velocities that the fluid feels as it goes around the Earth are much, much greater than the actual motions relative to the ground beneath the fluid. And that's really what you care about, because we want to understand, we want to understand weather patterns, we want to understand, these sorts of things, like local things that we observe on the ground traveling with the planet's surface. We already know the fluid is going around as the Earth rotates. That's not really important. So we actually, in this case, are going to write the F equals ma in an accelerating reference frame. And that adds in extra complications. The first one is the centrifugal force. So, which way is east? What is this way? That way is east? Carly? Yeah, thank you. So, as I'm standing here, you don't really feel it, but I'm traveling in this direction, according to somebody on Mars. I'm traveling in this direction, and I'm going really fast in this direction. I have an inertia. This is Newton's first law. Okay, objects in motion tend to stay in motion. I have an inertia in this direction, and I want to keep going in this direction. But the force of gravity is pulling me to the Earth, so I'm not moving. But as I go, that slight difference between the direction that I actually end up traveling and the direction that I'm currently propelled towards, these are different things. And so gravity has to work a little harder as it pushes me down towards the ground. It has to work a little harder to overcome my inertia, which is slightly directed off the planet. So there's actually a little term here in this gravity equation. We kind of just tuck it in to the gravity term because it's pretty negligible compared to the actual regular magnitude of gravity. But essentially, there's a little deviation which is just upwards locally relative to your position. Oh, sorry, no, that's not true. I should really follow my notes closely. It's not upwards locally. It's away from the planet's axis. So it's not in the direction of where you think the ground is. It's in the direction of away from the planet's rotation. So again, this is east, and then but the planet's axis is like there, right? Because I'm at 45 degrees latitude, or roughly so. So I'm actually, my centrifugal force is going to be acting like in that direction, or something. I don't know what. I mean, it's tough when you turn the windows closed, but whatever. Imagine that I knew which way east is. Then it's a little bit. It's like off in some other direction, away from the planet's axis of rotation. And if you were just at the equator, then that would align with where your feet are, and then this would just be all in the z direction. So that's why we can't just write minus rho g z hat. We have to do that little and tuck that centrifugal force into the g. Okay, so that's why it's written like this. Anybody have any questions? Perfect. Yeah, so in my notes I call this term gravity asterisk. Okay, next up, the Coriolis force. This is a big one. This is a very important one. So this is another fictitious force. Okay, so the centrifugal force and the Coriolis force aren't real. If you go to another frame of reference, they don't exist. They only exist because we're writing these equations from the perspective of a person who is accelerating. And that acceleration is represented as a force felt on the fluid, okay? So, essentially, if you were off the planet watching the winds blow around the Earth as they do, what you would see is, the wind is blowing along, but what happens is, it's not stuck to the planet, okay? The Earth rotates beneath it. This is a real headache, okay? So you have to write these equations, but you have to account for the fact that the Earth is rotating beneath the winds, and this extra term causes the fluid to get, when you're in the perspective, when you're on the planet, what you end up seeing this as is that the fluids get curled around in like big arcing patterns, and that curl goes normal to the direction of the velocity. To be honest with you, there's actually other components to the Coriolis force. But they're kind of, it's kind of inconvenient. We don't really care about all of them because we love to make approximations. So the atmosphere is actually very shallow compared to how wide it is. So there's a portion of that curl that goes vertically. But we don't really, it's not very significant because really the vertical motions you feel in the atmosphere, because it's it's most of the atmosphere, you consider 80% of the mass, it's like 10 kilometers deep, but then it's thousands of kilometers wide. So we don't really, just to make the math easier, we're going to neglect that vertical component of the Coriolis force, and we only consider the horizontal arcing that you experience from the perspective of the rotating frame. Now, okay, so I want to make a note here. As I said, this is a fictitious force, okay? So it has no effect on the energy. If you're ever writing an equation for the dynamics of a system, and you find that the energy changes from frame of reference to frame of reference, you have done something wrong, okay? The energy should be, as a Koch would call it, a Lorentz invariant quantity, okay? But that's a joke. You don't need to know what that means. Don't worry. It just means that everybody agrees on what the energy is. That doesn't change. Whereas the direction of something changes depending on who you are, which way you're oriented. The position of something changes, but the energy that doesn't move. So the Coriolis force, you can see here. Who knows what the vector cross product is? Yeah. Okay. Good. So as we all know, the cross product of a vector, of two vectors, gives you a third vector which is normal or orthogonal to both of them. So we can see here that the Coriolis force is orthogonal to the velocity. And as we all know, the way you write the work done on a thing is to write the dot product of the, to integrate as a line integral, the dot product of the force with the path that it travels, which is, of course, the path that it travels is parallel to the velocity. So this term does no work. It changes nothing about the energetics of the particle, of the fluid. And that is also true of the centrifugal term, although it's a whole mess, so I didn't want to write it. Okay. Anybody else? Any other good questions? Okay, we're making good. What's the time? Oh, cool. No, we're in good shape here. Marty, what's the thing that's good question. So, how could I forget? That is the Coriolis parameter. How could I forget? Thank you for reminding me. The Coriolis parameter. Again, so this is it's a little more complicated if you don't neglect the vertical, but luckily, we have no qualms about neglecting terms in our equation. So, the horizontal Coriolis force, it has a greater effect the further you are from the equator. So, anybody have a ball? You have so basically the way you want to think about it is if you're going along the surface of the Earth and it's rotating beneath you, then as you're moving, if you're at the equator, then it won't end up rotating beneath you horizontally. You're traveling tangentially to the surface of the planet. And so that rotation effect, the Earth rotating beneath you, the effect of that will be the same, it won't have any effect because the Earth beneath you is traveling in the same direction as you. Now, of course, there will still be a little bit of vertical deviation as you continue to move in this direction and the Earth goes off to the left or the right. But we don't care about that. Now, if you travel away from the equator, now the rotating Earth beneath you has some component that is moving in a different direction than your velocity. Okay, so if you're moving like here, I have a hard time explaining this stuff. It's kind of hard to think of, But what essentially this describes is, as you move farther from the equator, the Coriolis force has a greater effect. So this F here is a number which describes the rate of rotation, and it increases as you move away from the equator. If you were to write the latitude as a radian, theta, then you would find that F is equal to, is it 2 omega? 2 omega sine theta. This might be wrong. Don't quote me on it. But it's 2 omega sine theta, where omega is the rate, the angular velocity of Earth's rotation. Okay, so where theta is like 90 degrees or pi over 2 radians at the North Pole, and it's minus pi over 2 at the South Pole. And it's 0 at the equator. Okay, so that's what this describes. Now, as we can see, this will cause the Coriolis force to have a different sign depending on which hemisphere you're in. So if you are in the southern hemisphere, you get deflected. Okay, so the Z is up, and then the U, so you get deflected to the right if you're in the southern hemisphere by this Coriolis force. The Earth will tend to rotate you such that you end up going around in a circle like this. But if there's a negative sign attached to this thing, if there isn't a negative, if this negative cancels with this negative, if there is a negative, if this thing is positive, then that will go the opposite way. If your Z is still up, now your Z is down, and your U is still going, this is my direction, and now I get rotated, oh crap, I did it wrong the first time. Sorry, you get deflected left in the southern hemisphere and right in the upper hemisphere. The northern hemisphere. Okay, does anybody have any questions about that? Again, there's a lot of stuff. In the interest of time, there are little things which I'm trying to go for intuition, but there are tons of little things here which probably I have a 50-50 shot at answering if you ask me. So that's pretty good grade. I answered the F. I didn't get the D. Why is this a Lagrangian derivative? I don't know, but anyways. So the final term is friction. This one's pretty complicated actually because in the typical idea, friction just acts opposite to the velocity, and it's a dissipative force which kind of removes velocity, removes speed, and then adds heat. But there's all different ways to put that in. Essentially, everything in this fluid that causes it to act like a viscous, slushy fluid, that is contained in here. So it will drag along the surface of the planet. So the winds, because there's the ground there, and there's friction caused by the ground rubbing against the fluid. This friction term causes the winds to be much slower nearer to the surface. Also, if you were to write, again, this applies to any fluid. This formulation of it you wouldn't use to talk about a bathtub, for example. The Coriolis force, as we'll talk about in a moment, is not very significant on those sort of scales. But to talk about a very sticky, slow-moving fluid, which has long times to drop and these sorts of things, that will also describe all of those effects from the fluid being extremely viscous. But luckily for us, air is not a very viscous fluid, so we can pretty much just ignore that one. We love to do that. It's so fun to ignore terms in our equation. So now we can see a physical understanding for what each term in the equation means. So to summarize, that's just the acceleration and that's just the inertia, okay? This is you get pushed towards areas when you have when there's a sloping pressure. The gravity happens. The Earth rotates beneath you as you move around, and also you have some viscosity in your fluid. Okay. Of course, by the way, another note about the Coriolis force. It's a real headache. The Coriolis force. If you aren't moving with respect to the ground, then you're not going to feel any Coriolis force because you are immobile with respect to the piece of the Earth beneath you. And so in the equation, in the reference frame, which is following the rotation of the planet, you will not move. And so the Coriolis force depends also on the magnitude of the velocity. Okay. So now that we understand what this equation is telling us about how a fluid moves, how a fluid works, let's look at some basic solutions, okay? Now, of course, it's really hard to solve the Navier-Stokes equations. Usually we get the computer to do it, but it can be helpful and informative and fun to try to solve it with your bare hands, back like they did before they had computers. And the way we do that is we look at this equation and we say, wow, that's a really hard equation. There's like 5 terms there, and they're all kind of nasty vectors. This one you didn't even bother writing because it's too complicated. Wow, what a headache that would be. So what if, instead of it being this hard equation, it was an easy equation? What if that was the case? So let's say, okay, well, I already said, I don't care about friction. We're going to knock that one out. Let's say, where does friction not happen? As I said before, a large effect of friction is that if you're moving near a boundary, you will be slowed down. The boundary drags against you. So let's just talk about the section of the atmosphere which is away from that boundary layer, about, a kilometer or 2 per se. And there, you're going to find that the friction is basically 0. It's very, very negligible, okay? Let's also just talk about, as we said, the atmosphere is very shallow. So the vertical isn't really as important. We're mostly concerned about what is the horizontal transport of the fluid. So this one, I know there was the centrifugal, which apparently points not always vertical, but this one's basically just a vertical. So we're just going to talk about the horizontal component of the velocity, and we don't care about this one. Okay, so we can easily chop, without even needing to justify, we can chop off 2 terms. Now this isn't looking so bad, but it's still too hard for me. I don't know how to do that. So what I'm going to do is I'm going to do what's called a dimensional analysis, and a dimensional scaling analysis on the equation. So we wrote before that the big derivative of the velocity is equal to the time derivative plus u dot grad u. Okay, so let's just say for each function, or for each object in our equation, for each vector or scalar field, we can just kind of get a gross estimate for how big it is. And so for each quantity, we're just going to say, we don't really care about all that, derivatives and the complications that might cause. We just want to look at, what is the dimension of this thing and how big is that dimension? So in this case, for this term on the right here, I'll talk about this one in a second. For this term on the right here, we have a u times a u, and then there's also this derivative, which is going to have a 1 over length kind of thing. So it's going to kind of go, the u dot grad u is going to kind of go like u squared over L, okay? Now, the time derivative term doesn't exactly scale in the same way, but you can see it'll have the same units because this is meters squared, or meters per second, I mean to say. So then this will have units of meters squared per second squared, and then you divide by 1 meter. So it'll have units of meters per second squared. And then when you take the time derivative of a quantity with meters per second, it'll also have units of meters per second squared. And so in this case, you know, we can further justify this. Like this is going to be, if we have some quantity of time, t, then it'll be like over u, right? But then u is actually, we all know that velocity is equal to distance divided by time. So then if we want to write instead time is equal to L over u, and then we can put that in. So you can see that this term will also scale like u squared over L. Okay? Where's that? Alright. And then what we're going to do is we say, okay, this thing goes like u squared over L. We're just going to grab a typical velocity and a typical length of the thing we want to use these equations on. And we're just going to see, like, what is the size of that? And maybe we're going to get lucky, and hint, we are. Maybe we're going to get lucky, and one of these things is going to be like 0.01, and another one of them is going to be like 1. And then we can just ignore this thing. You know, it just doesn't matter at that point. It's negligible compared to the other terms in the equation. But in order to do that, let's get, how are we doing for time?
Maybe 10 more minutes.
10 more minutes? Okay. Are people content to take my word for it that the other term scales like FU? So, you know, it's the Z, that thing has no units. That's just a 1. That's a unit vector, right? So that just tells us about a direction. That doesn't have like a, I mean, it has units of length, but like, it doesn't have a size. It has size of 1. And then this thing is just like the F times the U, okay? So it's just the Coriolis parameter times the speed. We can do a similar, let's see here, okay. So the pressure term, it's kind of funny. The way you do this, you actually don't worry about the pressure term. It's all going to work out. So what we have is we're going to write a number. Let's just come up with a number. It's not going to have any units. We're just going to write a number, call it RO. And that number is going to be the size of the inertial term relative divided by the size of the Coriolis term. Okay? So that number is going to be, assuming our dimensional scaling analysis as we've discussed here, that number is going to be u squared over L divided by FU. And what we will find is that this number, which I claim gives us the size of, gives us the ratio essentially of the inertial force compared to the Coriolis force acting on this section of the fluid, is going to be U over FL. Okay? So that's pretty cool. Now, okay, so we said before that F, that is a bunch of stuff without units multiplied by the angular frequency of the planet. So F has units of per seconds or hertz. L has units of meters. U has units of meters per second. So this thing will have no units, okay? So what we have found, we have derived a non-dimensional number which describes a certain balance in the forces of our system. And depending on the value of this non-dimensional number, the different terms in our equation will be different. They will be more or less important. So if we were to set, let's say, this non-dimensional number, it's named after a guy named Rossby. Okay, so this is the Rossby number. If it's really big, that means that the U squared over L, the inertial term, for a really large Rossby number, that thing dominates, and we can get rid of this term. Okay? For a really small Rossby number, we can say that this thing is way bigger than this thing, and we can get rid of this. Now, luckily, we don't just have to worry about, well, I say luckily, I'm not so happy about this, but we don't just have to worry about theory and equations. We also can look at the Earth and see what's going on. So they tell me that you, in the upper atmosphere, in the mid-latitudes, which is where, we're not there, but that's like up above our heads, like some distance, U is about 30 meters a second. The winds get pretty quick as we go away from the surface, as I said. F, this is about 10 to the negative 4 hertz. And typical weather systems have a length scale of about 1,000 kilometers or 10 to the 6 meters. So that gets you that this Rossby number will be on the order of 0.1 for large-scale wind patterns away from the surface. Now, you might say, oh, well, 0.1, that's not very small. How do we know we can get rid of this term on a 0.1? Like, you're telling me this term is 10% the size of this term. That's not negligible. But I say it is, because, again, this is still too hard for me to solve. I got no other way to solve this. So I'm just going to say, goodbye. Now we have a really easy equation. Now our equation is, they also divide by the, let's divide by the, I didn't mean to cancel the row. You divide by the row before you do it. Yeah, because I didn't include the, sorry. You divide by the row. Okay, so now, this is our equation. This is called geostrophic balance. So this describes the large scale, again it's called geophysical fluid dynamics, geostrophic balance. I don't know what the strophic part means, but this is like large scale wind patterns are very well described by this equation. So we've just spent a lot of effort to look at every term in this equation and to understand what it means. And now we're tossing out most of them to get an easy equation that we can actually solve with our bare hands. Okay, so what does this mean? What's the actual intuition here? So what we're learning is that in these geostrophic winds, these two forces are going to be equal. The forces acting on a fluid parcel can be entirely summarized by these two balancing forces. Let's look at what that balance would look like. Okay. Let's say that you are a piece of fluid. Okay. Now, as you go along, let's say you're right here. Okay. Let's say you're at the edge of a very large low-pressure system, and at this moment in time, you aren't moving. So actually, this term will be 0, and all you will feel is the pressure force. Yes, Carly has a question.
Can you divide the row from the start to the row?
I don't like when you ask me good questions. Did I make a mistake? No. Am I? Hang on. I know this one's right. I think I made a mistake earlier because I wanted it to look, usually they divide by the row here. I wanted it to look like MA, so I kept the row, but I think I forgot to multiply the rows with every term. Ah, crap. So that's okay. So it'll actually be like, well, that one doesn't really mean anything. Yeah, okay, so there should be a row beside the Coriolis. Yeah, I guess so. It's not an exact science. It's not an exact science. Oh, crap. I'm gonna embarrass me in front of all. Okay, so let's go back to my hypothetical. So, as I said, you're gonna want to go down pressure, okay? So you're going to want to go into the area of lower pressure. Now what will that mean? Your velocity will increase in this direction. As your velocity increases, this term will no longer be zero. And so what will happen is, again, let's say we're in the northern hemisphere, so the F is positive. What will happen is your velocity will be going down here, and it'll increase in this direction. So the Z will be pointed up, and the U will be pointed like this, and then you have to, so the cross product says you'll go in this direction, but then actually you want to flip it because there's a negative sign. So what will happen is, as you fall into this low pressure field, you're going to get picked up by this Coriolis. As your velocity goes from being zero to not being zero, your velocity will pick up, and you will actually get balanced between these two forces perfectly. And so you will follow arcing trajectories around low pressure systems. So what will happen here? Now at each point on this vortex, there will be a pressure force acting down, or whatever, south, here, and then there will be a Coriolis force pushing it to balance that low pressure, which will act like this. And that will result, so it's not just the case that the winds always flow towards low pressure. The Coriolis force balances that pressure force and causes the fluid to flow in a vortex around low pressure systems. Now, as we go to situations where the geostrophic balance is a less valid approximation, this term especially will go away from being negligible. Also, well, this one too, I don't remember off the top of my head. But what can happen is the friction will break this geostrophic balance and cause, around low pressures, cause the fluid to pull inwards and converge in at the bottom of the low pressure system. And that will cause a lot of the weather which we experience. But we're getting to the end of our time. So I just wanted to show you that this all isn't a bunch of nonsense. These are very good approximations to the actual winds which we experience. Okay, so let me just, I know we're over time. I apologize. We started late. Now I'm going to show you actual model data from what people are using to describe the large-scale motions in the Earth's atmosphere. Remember, this thing's always thin, so.
You pull it down? Yeah.
You got it. Like first try. Oh, I think it's working.
Yeah.
Oh, perfect. Okay. So we have here the red is areas of lower pressure. Okay? And notice, if we zoom in, this is current. Now it's not actual meteorological observations. This is model data, but this is very close to what we actually are experiencing currently on Earth. So for example, back when Hurricane Maria was happening, if you went on this website, you would see a giant low pressure system right here, like a really big one. It was pretty crazy. That's how I learned about Hurricane Maria. I was just staring at this website. Okay, so apparently off the coast of Newfoundland, there's a low pressure system. And look at that. The winds are curling around it in a vortex. They're not just flowing into the low pressure, but they're doing, thank God I got the signs right, they're doing exactly what we thought they would. They're curling around, like the right hand rule, by the way, another win for the right hand rule. They're curling around in the right hand pattern And now these are the surface winds. So as I said, this isn't exactly, that's why there's some convergence there. This isn't exactly the balance we derive. But if you go to like 700 hectopascals or 850 hectopascals, you can see that that convergence doesn't really occur. What I mean when I say hectopascals, that's the pressure. So I'm going to an area of lower pressure, which means higher height. And what can we say? The equation works. I mean, that's what's happening. There's winds. They're flowing around a low-pressure system. Yeah, I mean, that's pretty much it. I just think it's neat that you can have this crazy fluid equation, and then you can throw out more than half the terms, get something that you can intuitively understand. And then it's actually like, this is basically exactly what is described in geographic balance. You have a question?
Can you see the other graphic line?
The southern hemisphere?
The, I'm like Asia.
Oh, yeah, sure.
It breaks down there. Marty's like,
I don't see any. I mean, okay, so the purple is lower pressure than yellow. You still see that, like, vortex shape. And now, okay, let's go to the southern hemisphere. And I'm pretty sure it goes in the opposite direction. Yes, it does. Because the F is the other sign. Thank you for reminding me about the Coriolis parameter. That was a blunder on my part. That's really good. Yeah, so now you have to do the right-hand rule. You have to tilt your thumb downwards because you're in the southern hemisphere. That's obviously how it works. And now it goes like this. So there you go. There you go. That's how geostrophic balance works. In full detail, pretty much. I can talk more about this, but we're really out of time, so, I mean, I'm finished. Okay, does anybody have any questions? No questions. Yeah?
so, if you get like close to the surface, is there like kind of a tractable way to see, like add back in the like friction and stuff to sort of see like what is like the tropospheric winds look like, or
Yeah, I think so. This is still troposphere, by the way.
or like lower?
But I know what you mean.
Yeah.
It's boundary layer.